Do you remember what a continuous function is?
It's a circle. It's not a circle.
A circle's not a function, but it is continuous. Okay, so let's talk through this then. Is this continuous?
No.
Yes.
No.
No, because we
Oh, it's got a break. Okay. Yes.
Fill it in
Okay,
and
so
then
thank you for the vocab word there. That's a point discontinuity.
A.
Does it change anything if I put the point on there?
No.
No, it doesn't. It's still a point discontinuity. Okay. Now we're starting to light bulb. Okay, how about something like this?
No.
Jump discontinuity. Yes. Okay. Are there any others?
What about the one that's like
Mason.
If the blue top was filled in, would that still be a jump discontinuity?
Yeah.
And it would not be a function at that point.
Not yes.
Right.
Exactly.
Okay, so yeah, that's still a jump. Anything with a break like that. There's one more type.
Continuity.
It's just a line with this orange. I don't know.
You guys disappoint me.
Is it where it just stops? Like,
Oh.
What's that called?
Infinite.
Thank you.
Wow,
My hope is restored.
What hope? I know, it's like-
There's always hope.
One of the practice problems is kind of like that. Like they really like infinity stuff. But
Infinite discontinuity. Okay, so what do we have to have for a function to be continuous? That's the question of the day.
so how do we get infinite discontinuity?
So what has to happen? What did that first one violate?
There's a break.
There's a break in the
There's a
middle.
break with a point, right? So that point has to exist, correct? Okay, so the point must exist. Yeah? So, let me just. So we have a point that exists. Now what has to happen? The line has to go through the point. Yes? Like that. And that is very basic language. Goes through the point. Okay. Have I still satisfied the jump discontinuity right here? Does that line go through the point? And the point exists?
Yeah, right, it goes to it.
Goes to it. Okay, so you're using your language skills. Thank you. How can we say this in terms of calculus? That's the question. Okay. If a point must exist, if we have a function, this is x, and this is y, how do we note the point must exist? F of x equals y. Okay, so that's this right here. Right? The point exists. You plug it in, it gives you a number. Okay? Equals. Okay. How do we know in calculus that the line goes through or to? He's on it today, man. He's like,
He doesn't yell during our class. He's very.
microeconomics.
As
Oh, you're still in government, aren't you?
Yeah, that's Gov and we had Gov.
How can I show in calculus terms this line goes to and through that
As
point?
line approaches from the left equals blank, and as it approaches from the right equals
What do we call that in calculus?
limit.
The limit.
The limit doesn't-
So the limit as x approaches,
X negative.
that's terrible notation. I'm going to change that to a C.
X approaches X.
Limit as x approaches C of f of x equals what?
Y.
The y value. Okay? That's how you show continuity in calculus. And this is the definition. Like last year, you know how we did those tables? The numeric limit? You remember that? Last year we would do the table and it would have the C value here, and you'd have to do all your numbers this way and this way.
Oh, yeah.
You were calculating limits and you didn't even know it.
I knew this was similar.
Okay? We have methods now that are much easier because you have the language and you have the plug and chug and you'll have the algebra and okay, so continuity becomes actually easier in calculus because of the tools that we have to solve that equation. Okay, so let's formalize it. I'll show you an example. We'll work through it. It is a definition that you should have memorized. Okay, because it will show up on the test. All right. Let's make it real easy for this. Show this function is continuous at x equals 3. Okay. Very straightforward. We'll just solve the process. Okay. And then I'll show you a piecewise function where we have to go into touch more detail.
So we just put in 3.
Okay, so yeah, what's the first step there? And I always do 1, 2, 3.
Plug.
F at 3 is?
9, 6, 15.
Okay, 15.
Why are you looking at me like I'm
Well, you
dumb?
said 9, 6, and 15. I'm
Well,
like,
yeah,
which
'cause
one
9
is it?
plus 6
I
is
get
15.
it. No, I had to think about it, but I get it.
Getting that hip lingo in this
You bet. Be so gangster here.
Oh, God.
All right, now we have the limit as x approaches 3 of f of x, which equals 15, because we can plug and chug this one, right? Okay. At this point, we know it's continuous. We know f is continuous. Specific language. We just have to make that statement. Okay. Since f of 3 equals 15, and there are a couple ways to write this part. And I always write which equals the limit as x approaches 3 of f of x. Just one statement, right? Shows they're equal. F of x. Yeah, that's my limit signature.
Yeah.
Remember?
Sounds like
As
Sam.
long as there's an L that's cursive in front, we know exactly what it is. F of x is continuous at x equals 3, right?
So is that a since or like those are
Done.
Is that or you need both? Don't they
You
say
need to
same
put
thing?
both of these here.
Oh, you do?
Somewhere. You could write that Or you could write that. Either one works. You just need to show their equivalent some way. Just state it. Okay? And yes, I know it's stated up here. In all honesty, you could probably say, therefore f is continuous at x equals 3. Right? But we want to be specific in structure because honestly, we put this in here because AP,
Is that plus or minus x?
they kind of waffle on it. So this covers our bases.
Oh, I thought it was positive over.
No, that doesn't.
Dot plus x equals 3.
Plus divide.
Okay. Dot plus multiplies equals 3. Yeah, no, not anymore. So that's an easier example, right? You can handle that? Again, it's just a process. Know the process. All the processes are not hard. You just got to know how to use those. Okay? Are we good?
This one shouldn't have been so much easier than last one.
I know. Which it just kills me to do that every year. I'm like, this is
You're
ridiculous.
just like, I'm filling your
But if I
brain
said the
with
word limit,
Don't worry,
like-
it's so much.
Yes,
okay.
yes. All together every year.
Whatever language.
We kind of learned it.
Whoa.
Okay, piecewise functions and continuity. This is usually how they will present it to you in the AP exam. Okay, so we address it and we work it. And we smash it with a hammer. And then it's not continuous anymore. I'd still be there. It just wouldn't be in the same condition.
So yes, we still be continuous.
Why'd you say no instantly?
Yeah,
That
why?
makes sense. What?
You guys, it's
Something.
greater than one? And because it's less, well, it can be less than a.
It's greater than and less than 1, so no.
Okay, those are the x values.
X is
Right.
less than 1. And then
So if
you
x
have
equals 1 is right here, correct?
Okay.
It can be
So
greater.
what's f at 1? Is 3, okay? But this is what I'm saying. Follow the process. This is how you have to disprove or prove. Okay? Now the limit.
Are we gonna spell it continuous? It's just looks wrong.
Continuous. No, it's definitely right now that that's an S.
It looks like a 5.
It's not 5.
Look at these.
Okay.
Good thing I can read.
The two-sided limit. Can I just say the limit exists or does not exist?
No.
I cannot. I have to do the left and right limits.
Ah.
Okay, so the limit as x approaches 1 from the left. Which one of these does it use?
Use 3.
It'd be,
I mean,
Which one comes from the left?
X.
I'm not sure, it's less than 1.
That one, right there.
Yeah.
so it's like
Okay.
a.
Right. The left-handed limit comes from
That.
where it's less than 1. So plug 1 in here. Okay? What's the right limit?
Whenever x is greater than 3.
This is where it comes from the right. Yes?
So it'd be 3.
The answer is 3.
So x,
Oh, so it's 1.
So the two-sided limit,
Okay, that makes sense.
what's the answer?
2.
Does not exist. Okay.
You gotta prove why? No. Can't just
So
say-
this is where piecewise functions get a little bit more detailed. You're still doing this limit, you just have to use the left and the right to show it.
Wait, I don't understand the D and E part of that.
These need to match.
Oh, they have to match?
Yeah.
Oh, yeah, yeah, okay.
So they both.
And to be continuous has to match. all three of these.
Chunk
But,
discontinuity.
yeah, so you're just trying to show that it's not continuous by using the limits. Okay, one is up here, one's down here.
So,
Jump
so
discontinuity.
does that mean that it becomes discontinuous around one?
It is discontinuous at one.
Coming from one?
Garrett,
I'm confused of what equation we use when it
Okay.
comes from the right.
if you look at a number line, here's one, correct? This function for x less than 1, the value we use is x. That's from the left side. We plug our limit into x. So if the limit is x approaches 1 to the left, it's 1. Okay. If x is greater than or equal to 1, the answer is 3. So if we're coming from the right side, the right-handed limit is 3.
So what is the bottom equation for?
We haven't used it yet. It's a different one. So we would come out here to 3. This would come over, solid dot, and again, out here we would have x. Okay. So at this point here is f continuous. Is not continuous
So you can enter D and E.
at
There we go. We have all of these variations, all of them abbreviation
abbreviation nation. Welcome to math. Okay. How about at x equals 3?
It does exist.
What is f at 3? Yeah. That's the equals 3 here, so 3, right?
Yeah.
Okay, that's first step. Okay, what's next? Limit as x approaches 3 from the left. Okay, which one are we using?
Middle line.
Middle. X is less than 3, right? Less than 3. So the answer is 3.
So the
Now from the right, we're greater than 3. Use this function, right? Plug 3 in, you get 3. Now you can see that it is.
Wait, how do you know it's three?
We approach 3 from the right with this function here, right? So your limit, if you write it out with that in there, limit as x approaches 3 from the right. And now it's plug and chug. Use this function.
So it'll be three here.
Right. So you can write this either way. Okay, it's just standard notation. Does that make sense? I hope so. You look a little confused still, but.
Because the bottom one is like x greater than 3, so you put
Yeah, so greater than on the number line is to the right, correct? So if your limit is from the right, that's what you use. State, I just get in a habit of doing this. The limit as x approaches 3 of f of x equals 3, right? Then make your statement. Since the limit as x approaches 3 f of x equals 3, which is f of 3. F, don't write it. Okay, there's an it there, and there's an it there, and there's an it there, and there's an it there. They're gonna assume you have no idea what you're talking about. F of x is continuous at, and there's always an at. Okay. Yeah, that would actually, if I drew the graph correctly, it would be continuous. Oh, yeah, I was just drawing it. This is not the graph. This is just a number line. Okay, the graph actually is a coordinate plane 1, 2, 3, right?
Got it.
So from 1 to 3, the value is 3, y equals 3. Here, and this is a hollow dot. So y equals x on both sides with y equals 3 in the middle. Right. Okay, so that's continuity. Let's talk about one more thing around it, and we'll be done. This will not come up on the AP exam, but it's handy at times, and your book addresses it pretty heavily, so I just want to mention it. Is g of x continuous? No. But it is what we call left continuous.
Time.
Because the one that left side doesn't stop.
Because we have a dot there that's solid, right? Okay, the point exists. G of x is not right continuous. Because the dot is hollow. The point does not exist. Point D N. Okay. In calculus terms, the limit as x approaches 1 from the left of g of x equals 2, right? From the left side, which also equals g at 1. Right. So you're just saying the limit from the left is the point. In calculus terms, the limit as x approaches 1 from the right is 2.9. If that works. 2.5, which does not equal 2, which is g of 1. There's not a match. Okay. Yeah, so it's not continuous. G of x is not continuous, I should say. Okay.
I have a question.
I hope I have an answer.
Can you have something that's left continuous and right continuous but not completely continuous?
Yes.
So if that dot was filled in, it would be left and right continuous, but also not continuous.
That would not be a function either.
Like,
Yeah. But yeah, you can do this. Left and right continuous, not completely continuous. I think that's a good thing. I'm glad you mentioned that because you're going to have problems this year that say, can this happen?
No.
Must this happen? Okay, can it be left and right continuous?
Yes.
Does that imply it's continuous?
No.
No. You need to think in terms of that at times. Always be a problem solver and a thinker. Conditions. Okay. All right. We're good. I hope we're good. Okay, there are some prelims here now that I want you to do. And then the exercises. I picked those very specifically. Again, let's do tomorrow. So we'll check it. Tomorrow we'll continue working with continuity. We're just going to talk about specific functions and their continuity, like polynomials and sine, cosine, and tangent. And it serves us well to know those just off the bat. Okay. Do you need anything to graph it? Two, three, no.
Chapter 10, subchapter.
You don't need to graph any of these. You can all be done algebraically, just like we did today. Yeah.